Hi, I'm Bobby Ashworth, and I'm in Dr. Buckner's MAE 535 class, and what I'm going to attempt to do today is to demonstrate the effects of eddy currents used in common household objects. Okay, here I have a pendulum that I spared no expense in creating. What this pendulum is a toilet paper tube with a series of aluminum foil strips bound together. What I did was I took aluminum foil and folded it back and forth over top of each other to create a fairly solid piece of aluminum. And what I'll do is swing this back and forth under a magnetic field, and hopefully we can see what happens. To start with, I'll use these ceramic magnets. I picked these up from Radio Shack, and these are not very strong magnets, but they do have a slight effect. And I guess I'll start by putting it behind the field, or behind the plate rather. So you can see I'll rock it back and forth here without touching it, and see what kind of effect this has. Now you really can't see it, but I can feel a slight force coming about on the magnet. Try that again. Okay, this is neither effective or exciting, so what I'll do is put these down and try it again using this rare earth magnet that I borrowed from a Faraday flashlight, and try and repeat the process. Again, trying to hold the magnet as close as possible with actually touching the piece of aluminum, and then rocking it back and forth. Now, this is a much more pronounced effect. I can really feel it, and you probably can see it too, how it kind of damps down. Oh, pretty strong magnet. And I also can move the magnet here across the plate, and the plate will move with the magnet. Bear in mind here, I'm not actually touching the plate. And that is what I think is the most effective eddy current demonstration. Okay, what I'm going to attempt to do here is to demonstrate the effect of eddy currents on ordinary pocket change. This is just change that I grabbed from my pocket today. And conceptually, what we're going to be looking at is something like this. I'm going to have the coin atop of the magnet, and I'm going to move the magnet with some velocity into the coin, and in doing so, it'll produce these little eddy currents about both halves of the coin. So what that'll look like is something like this. And we know from first principles that anytime you have a current flowing, that also generates a magnetic field of its own. So conceptually, what we'll have here is a magnetic field going into the page and a magnetic field going out of the page at both the top and bottom. This is generated using the right-hand rule about these currents. So that's top and then bottom. So it's out, that's in. This is consistent with what I've drawn here. And remember from before, our magnet was going into the page. So our magnet here underneath going into this, these two have like poles, so a north to a north or a south to south. And another one, they have opposites. So as the magnet is moved, it'll repel or push the top half of the coin, and then the bottom half will want to be with the magnet, so that'll follow and actually be force behind it. And let's see that. Here I've placed the coins that I had before in this little plastic tray, and I did this in order to put the magnet underneath without actually contacting the coins. As before, these are the same coins I had before. Notice they're not trick coins made out of steel or some actually ferromagnetic material. And what I'll do here, again, is pass the magnet underneath, and that'll hopefully catch and drag the coins as predicted before by this diagram. So like charges repel, which will push the coin. Opposite charges attract, which will pull the coin. So the net effect should be the coin should follow the magnetic field. Okay, so we can do this. All right, first the quarter. All right, now the dime. And now the penny. And the nickel. Alright, nickel's not doing too good, so possibly that's different alloy. Notice too that the direction of the magnet doesn't matter, so I can either do, I guess we'll call this north, and that causes the coin to follow, or we'll call this south, that causes the coin to follow. I don't really know which is north, which is south on this, but the net effect of the eddy currents doesn't matter. So, in summary, the faster you move the magnet, the stronger the eddy currents, and the easier it is for the coin to follow the magnet, versus moving slowly across it does not have as strong of an effect. Likewise, too, we can use a weaker magnet. Magnets have to be attracted to each other here. A weaker magnet to try and demonstrate the same effect. This is the ceramic disc magnet I got from Radio Shack. And no matter how fast I move this, I really cannot get an effect on the coin. So, observations are consistent with the theory that the stronger the magnet, the stronger the eddy currents, and the more resistance to motion, or in this case, the easier it is for the coin to follow the magnet. And also, the faster the motion of the magnet, the stronger the eddy currents, and the more resistance to motion, or in this case, the easier it is for the coin to follow the magnet.